Okay, so let's say that we have a large disk, and let's say that it has a radius of 0.5 meters. So this is a 1 meter large disk. Say that it has a mass of 2 kilograms, and let's say that it's rotating with an angular velocity like this of 2 radians per second. Okay, now for this disk, I want to calculate its angular velocity, or its angular momentum, but there's just a lot of particles here, right? Too many to add up all the angular momentum, though, because that's just, we'd have to add up a whole bunch of r cross p's to get the total angular momentum there. Okay, so what we can do is we can think smarter here, and so remember that r cross p is equal to m times r cross v. Okay, and we can replace v with omega times r, and in the case of this, the v is tangential to the circle, which means that the r is perpendicular to the velocity, which kind of resolves the cross product here for us. So we get that this is equal to mr times, so that we can get rid of the cross product because these are perpendicular, times omega times r. Okay, let's rework this a little bit. We're finding the sum of all these. Okay, so that means that we're going to get the sum of mr squared omega. Okay, now in the case of a circle like this, where everything's rotating together, then omega is the same for all of them. So it'd be equal to the sum of the mr squareds, okay, times omega. Now before we continue, take a look at this, okay? Does that piece look familiar to you? Alright, maybe from our last chapter, finding mr squared, what does that represent? Okay, well, if we find the sum of all the mr squareds, that's the moment of inertia. Okay, so if we multiply our moment of inertia times our angular velocity, that gives us angular momentum. And for some reason, for a rigid body like this, instead of a particle like this, we use a capital L. So to find the angular momentum of this object, we use I times omega. Okay, and think about this. So linear velocity, linear momentum is mass times linear velocity. Okay, angular momentum is the angular version of mass times angular velocity. Okay, this is just another correlation, another analog like we've been seeing. Okay, so if we want to find the angular velocity here, it's a uniform disk, which means that I would be equal to 1/2 mr squared. Okay, so L would be 1/2 mr squared, and then we're multiplying by omega. Okay, so let's plug in our values. So 1/2 times 2 kilograms times 0.5 radians per second squared times, 0.5 meters squared, okay, times our angular velocity of 2 radians per second. Okay, I multiply all these together, and I'm going to get, let's see, this would be, I think, 0.5 kilogram meters squared be equal to L. Okay, so we found angular velocity of a rigid object, or angular momentum rather. Let's go ahead and practice it. Okay, so here is a meter stick being twirled about, let's say, just its center of mass. No, let's say it's being spun around one end, okay, just to make things more difficult. Okay, so being spun around one end, it's a meter stick, so it has a length of 1 meter. Let's say it has a mass of about 60 grams or 0.06 kilograms. Okay, and let's say that it has at this moment an angular velocity of 2 radians per second. Okay, so let's find the angular momentum of this object. Okay, so L equals I omega. Since this is a uniform rod, we can use 1/12 ml squared, but since it's off center, we have to use the parallel axis theorem. Okay, go ahead and find the moment of inertia of this rod before we continue. Okay, so what you should have gotten, it would be 1/12 ml squared plus mh squared. Okay, so that's 1/12 times 0.06 times 1 meter squared plus 0.06 kilograms times 0.5 meters squared, because a half of a meter is our distance from the center of mass. Okay, and that's all times omega. Alright, so we punch it in. Okay, so we get a moment of inertia of about 0.02 kilogram meters squared times 2 radians per second. So this is going to give us 0.04 kilogram meters squared per second for our angular momentum. Okay, one more example we're going to do, okay, to kind of just show how we could put all these pieces together, okay, and that will be, then we'll move on to kind of the last topic. Okay, so let's say now that we have a merry-go-round like you see at the playgrounds, let's say it has a radius of about a meter. Let's say that, let's say this. Let's say that there's a kid that runs and jumps on it. This kid has a mass of 2 kilograms. Let's say he's running to jump on it. Okay, sorry. His mass is greater than 2 kilograms. Let's say his mass is 50 kilograms. Okay, and let's say he's running with a velocity maybe of 4 meters per second. Okay, so as he's running towards the merry-go-round is currently rotating with an angular velocity this way, a negative angular velocity of -1 radian per second, and this merry-go-round has a mass of, let's say, 20 kilograms. Okay, and so we have the boy running this way, the merry-go-round spinning this way, okay, has a radius of 1 meter, and we want to find the angular momentum of this system. So that's going to be equal to L, and for this we're going to have to add L of the merry-go-round plus L of the child. Okay, so we know that we can find L a lot of different ways. L is equal to I omega for a uniform object. It's equal to R cross P for a particle. Okay, it's also equal to the integral of torque with respect to time. Okay, and so these are kind of 3 different ways we could find this, and for each piece we're going to have to decide what to use. So let's start with the merry-go-round. Okay, which of these 3 do you think we should use and why? We should use this first one here because it's a uniform object. Okay, every piece on it is spinning at the same speed. It's moving in a negative direction, so we'd say it has a negative angular momentum. Okay, we could use that -1 for the velocity. So it's a disk, so that'd be, so I omega would be 1/2 m r squared omega, so 1/2 times our mass of 20 kilograms, our radius of 1 meter, and our angular velocity of -1 radians per second. giving us for the merry-go-round itself a moment of inertia, a angular momentum of negative 10 kilogram meters squared per second. Okay, now we haven't added on the other piece yet. We need to now find the angular momentum for the child. Okay, so for the child, which of these three do you think we should use, and why? Okay, so for the child, since we know the mass and since we know the velocity and they're running, we don't have any information about the dimensions, so we're going to assume that we can treat this child as like a particle, so we would use this one, the r cross p. Okay, so r cross p would be m times r cross v. Okay, and so it has a mass of 50 kilograms, has a radius of 1 meter because they're going to pass within a meter of this rotational axis that we're using. Okay, and that's perpendicular to their velocity of 4 meters per second. Okay, so this child will have an angular momentum of 200 kilogram meters per second. Okay, so negative 10 kilogram meters per second plus 200 kilogram meters squared per second. Okay, we add those together and we get 190 kilogram meters squared per second for our angular momentum of this system here. Okay, so let's go ahead and kind of look at a little summary. So you may have seen this in your book, but it kind of summarizes all the rotational analogs we've seen so far. So we know that force and torque are similar. Okay, torque is like the rotational version of force. Angular momentum is the angular version of linear momentum. We can find the linear momentum of a system or of a rigid object by adding up the momentum of all the pieces. Same with angular momentum. We can find the momentum of a large object by multiplying its total mass by the velocity of its center of mass. We can find the angular momentum of a rotating object by multiplying I by its angular velocity. Force is the rate of change of linear momentum. Torque is the rate of change of angular momentum. And now we have this last piece here. Okay, and this is probably the really significant piece. Okay, the total momentum of a system is constant. Okay, for angular momentum, the total angular momentum of the system is constant. Now, this is probably one of the most powerful concepts that we're going to talk about this whole year. Okay, this is kind of, I mentioned this earlier, it's hard for us to just really grasp how significant this is and how powerful angular momentum is and the conservation of angular momentum is. But as we explore it, hopefully you can start to get an idea about that. Okay, and so the next couple videos will be about the conservation of angular momentum.